Alright, so Hooke's law, and there may be a little bit of jitteriness to the video, but let's see how it works out. Hooke's law, and I'm going to take right off the video there, describes the relationship between two variables. First variable is the restoration force. The restoration force. Of a spring. And the amount of length that it's distorted by. Right, so the two big variables that we're looking at. How much a spring is distorted, and what force it takes to distort that spring. So I could take a look at a spring here, and I got a spring in the lab. If I take this spring and I pull on it, it gets stretched. And if I let it go, it relaxes. Every time I apply a force, its length changes. Okay? So what I could say is that if I have a spring, let's say hanging from the ceiling. I happen to have a spring hanging from the ceiling today, so I'm going to illustrate this spring hanging from the ceiling. If I have a spring hanging from the ceiling with no forces acting on it, then we say that it has a rest length or a relaxed length. Okay, and I always like to have a spring hanging from the ceiling in case I ever want to get into a conversation about Hooke's law. So it's the rest length of the spring. If, on the other hand, I take the same spring, I'll do it in red, the same spring, and I hang a mass off of it, you tell me, what happens to a spring if I hang mass off of it? What happens to that spring? Yeah? Yeah, it stretches. Now, it used to be that our spring was a length of L, but now it's L and then some extra. And so people talk about that extra bit as the delta x, the amount that's changed in length. And that's the part that we've underlined here. I'll underline it in red so that it matches the length that it's distorted by. Now the spring that I have hanging above my head right now, like this one here, is what we would call an extension spring. An extension spring is a spring that stretches. And I can write the word extension if you like above it, just to remind us. The spring above my head is not a spring that could compress. But if we could compress it, if I had a spring that could compress, because the one that I have, all the coils kind of bump up against each other if I have it at its rest length. You can sort of see that if you're looking at the one above my head. But if it could compress even shorter, it might look something like this, a shorter spring. So this is kind of a unchanged, pull down on it, push up on it. And I can pull down on it really easily with a mass, but if I'm talking about the spring above my head, it's hard to think of what I would use to push up on it. You might use a person, depending on your mood. I feel kind of like gnomes today. That's a gnome with a pointy hat pushing up on a spring. Whatever you use to distort your springs, you should be able to know how much force that distortion device or person or whatever is able to exert. So I have this little gnome pushing up on the spring, and what I'm going to say is that the spring used to be a length of L, just like we said before. What would I label this amount here? What do you think? Yep. Yeah, it would also be delta x. It's just that it's the delta x for what we're going to call a compression spring. Because we're just talking about the length that it's just been distorted by. That's the delta x value. And you know what? Just for kicks, just to color code, I'm going to underline it. Oops, wrong color. I'm going to underline it in green as well. That's how much we've distorted it by. Okay? All right. Now, I know that with the spring above me, I could add, and I'll do this just off to the side here, I could add, so with an extension spring, more and more mass. I want you to predict for me. If I added a second mass onto it, what would it do? So let me in the lab at least, let me add my first mass. Where'd all my masses go? Holy smokes. Oh, thank you. If I put one mass on it, it hangs. It bounces a little bit unless I hold it. If I put two masses on it, tell me, what are you going to see? Somebody says hangs lower. It's true, it hangs lower. Something like that. What happens to the delta x value when it hangs lower? Yeah, it increases. Now the L value is still the same, but we've got a bigger delta x value. So you know, whenever you do experiments with springs, when you're trying to do work with Hooke's law, you got to measure the rest length, the unstretched length of your spring before you start. That's really important, because what you always care about is the change in length, that delta x value, okay? That's really important for this kind of analysis. So I want to take this sheet and just push it up a little bit. Start on a new page. Start fresh. And I want to propose that instead of having, oh, I didn't add a second mass on there. Instead of having one mass and just two masses, I'd like to say that it could be possible. Maybe I could set up a table for myself. I could call it Table 1. No, because it's the first table I've drawn today. Table 1. Force and distortions of an extension spring. That's not a beautiful title. It's not lovely. It doesn't get into the lustrousness of the spring, the beauty, the passion that I really feel for springiness and all things elastic in nature. What it is a description, okay? If you just write Table 1, Observations, that is not a descriptive title, and you will not get a mark if we're talking marks type of things, okay? You gotta have a descriptive title. I say it once, I say it a million times, and every single year, people write me a Table 1, Observations. And I say, ah! Makes me want to cry inside. Anyway, a nice title, a nice table like this, you might have one column header might be force applied, or we might call it F, and you might have units of newtons. Some people want to call it not force applied, but spring force or something like that. That would be a nice descriptive header. You know, we could call it lots of different things. But I'm going to apply a force using hanging masses. Some people want to be even more descriptive. They'll say force applied by the force due to gravity acting on hanging masses. Sure, go for it. I'm going to keep it short this time, okay? Spring distortion. And the associated variable might be delta x. What would be good units for delta x, by the way? What are the length units we always use in physics? Yeah? Meters. Bingo. Bingo was his name. All right. So let's say that we did an observation table like this. We filled it in, and we took springs like this one, and we kept on hanging more and more mass off of it, more and more successive mass. And the way that we got our force values was that we recognized that the applied force was always the FGs that were acting on these hanging masses. And so we could find out all these FG values. And let's say that the first one was 5.00 newtons.
Excuse the interruption, Mr. Killens.
Hi there.
Hi, can I see Calvin for one moment in student services?
Sure.
Thank you.
Oh, it's not here. Calvin's not here. Can somebody run down to student services to let them know that Calvin's not here? Oh, thank you so much. And now it's on video that Calvin wasn't here. All right. Now, I made a mistake here. What was my mistake? There's something critically wrong in my observation table. Yeah? Well, actually, you know what? The fact that they don't all have the same significant figures isn't really an issue. What I look at here is that whatever my measurement tool was, I'm claiming that I was accurate to 2 decimal places, which actually might be reasonable if I use 9.81 meters per second squared as my acceleration due to gravity, right? So significant figures isn't an issue. It's actually the decimal places that I want to have in agreement, so I'm glad you pointed that out. The other thing is units. I wrote units there. I don't have to. Why don't I have to write units in green here? Yep.
It's in the header.
It's in the header. They shouldn't be there. In fact, it's wrong. It's redundant. Get rid of those things. Okay? You should just have numbers if you have your units in the header, and that's what you should have, your units in the header in round brackets. Now in the next column over, I'm going to make up some data. Let's pretend that I hung masses from my ceiling, you know, successively more masses, and the spring, as you'd predict, gets lower and lower. I'm so scared. And it gets lower and lower and lower, and the spring in the classroom is getting more and more mass on it. You can't see it on the video, so sorry. Let's see if I can do it. That's me. Oh, there's some masses hanging from the ceiling. They're getting lower and lower and lower. Anyway, I don't want to look at that anymore. Back to the note. Oh, how do I get this video camera back on here? Alright. Looks like Blair Witch Project. Oh, that's a dated reference. Alright. What's that? Oh gosh. That was a mistake. Maybe I'll edit that out. Probably not. All right. So for everybody that's having a seizure right now, I apologize. All right, we're back. Now you've seen a hanging mass. You feel like you've lived a little bit. Let's say that we hung more and more masses on this thing, and what we saw was that after the first mass got hung, the stretch length ended up being 0.020 meters longer than it used to be. Oh man, I did it again. Naughty, naughty, naughty. Units shouldn't be there. Let's say that the second time I measured the stretch length, I ended up getting 0.040 meters. In other words, 4 centimeters. What do you think the next one would be? What do you say? Why would you say that? It turns out that it would be about that. Okay, experimentally it would be about that. Assuming that our string is ideal, it turns out that if our forces went up in equal increments, the stretch should go up in equal increments if this is an ideal spring. What we're claiming is that the force that I apply to a spring is proportional to the amount that it stretches by. In other words, if I apply more force to a spring, it's going to stretch more. If I apply less force to a spring, it stretches less. Now you guys are going to do an experiment like this. What you're going to do is actually measure force values using masses, or find force values using masses, and measure the distortion amount using a ruler or meter stick. And you're going to come up with a table of values like this. What you could generate from this data is the following. If I put the force on the vertical axis, and I put the delta x values on the horizontal axis, and I actually plot these data points. Now I'm not going to take the time to plot the data points accurately or set a scale for this. This is just for purposes of showing you. If I were to get a scatter plot like this, where the axes had been set up properly, with the proper units, labeled effectively with a scaled set of axes with all the numbers written in there, what am I missing from my graph? Yep. Line of best fit. Beautiful. I've used red and green, which looks like a Christmas theme, but really it's spring, so I should have used something more like flowery or something. Yeah, for people doing this in first semester, This is being recorded in second semester, and spring has sprung. Okay? Ironically. Thank you to the seasons for being in sync with us. Anyway, what you need to have for this, if I'm communicating it, before I get into the analysis side of it, is a title. So you don't need the flower. But graph 1, it's the first graph I did today. So graph 1, and then some descriptive title. Okay? It might be very similar to the table title that you did earlier. Once I have the graph, though, I can do some analysis. And every time I have a line graph like this that goes through the zero, through the origin, I want to make sure that the fact that it goes through the origin makes sense. Does it make sense that this graph goes through the origin? Somebody tell me why it makes sense. Yeah?
Because with no force, then the spring will stay at the same length instead of no extra X.
That makes a lot of sense. What she says is that at that point there's no stretch amount, and that makes sense because it also means that you haven't applied any force to it. You never want to force a graph to go through the origin if it doesn't make sense. Okay? Certainly this data shows that it should go through the origin, but it totally makes sense that it should go through the origin as well. The other thing I like to look at in terms of making sense of a graph, what is it? Find the slope. I always like to find slopes whenever I have a linear graph. Makes me feel good inside. And so I have a rise and a run. And when you do graphs for a lab, I'm going to require, this is my requirement, for full marks for analysis, that you label the rise and the run for the points that you've used to calculate your slope. And what's more, the rise and the run labels should draw out a triangle, and that triangle should be large by comparison to the graph itself. If you do a little bitty triangle like this one, if you're off by a little bit with your points, that's going to introduce a huge percentage error with your slope calculation. If you make a big triangle and you're off by a little bit with your points, that introduces a smaller percentage error with your slope calculations. Never do a tiny slope triangle. Call it a rate triangle. You will lose accuracy marks, okay? I'm telling you that right off the bat, so there's no debate about it, okay? Anyway, we have a rise and we have a run. And every time I'm able to find a rise and a run for a slope, I always think of that good old grade 9 equation, y equals mx plus b. And when I look at this equation, I can see right off the bat, what's the value of the b? 0. Bingo was his name-o. What's the variable on this graph that represents the y-axis? Yeah? Force, yeah. We can call it force applied, but I'm just going to call it force. M is the slope. And actually, conveniently, instead of saying x, this time the x variable is being represented by the delta x-axis. It turns out that this slope here talks about how stretchy or how much force it takes to change the length of the spring. It's a part of the relationship. So Hooke's law says that the force applied to a spring or a linearly elastic material will be proportional to the amount that the material stretches by or is distorted by. Okay? Instead of saying slope, what people have said is F equals K times delta X. K stands for constant, if you're really phonetic, I guess. But this K, is it going to be the same for every spring? What do you think? No. Every spring is going to be a little bit different. Here's the question, though. If I have a steep slope like this one, I'll draw another graph on the same set of axes. A steep slope like that, which one of these springs is stiffer, the pink one or the red one? Which one's stiffer? Which one takes more force to have the same stretch amount? Yeah. The pink one, yeah. And you know what? I could draw a little line up here. I'll do it in green. Let's just say that this was the 0.04 meter mark. That's how much it was stretched by, 0.04 meters. Can you see that the pink one requires more force than the red one does to get it to distort by 0.04 meters? That's the way I would read a graph like this. I would look up this green line, check to see how much it's been stretched by, and recognize that the pink one needs more force to get the same stretch. And in my vocabulary, that means the pink spring is stiffer. You might say the red one is stretchier. Likewise, if I had a graph that was less steep than the red one, that one would be a stretchier spring. That just makes sense to me. Okay? And if it doesn't make sense to you, then we should talk about it afterwards. Okay? Definitely. Now, there's one more feature about this equation. Many people like to put a negative sign in front of the k. The reason they like to put the negative sign in front of the k is because they want to remind you that if there's an applied force because of a hanging mass, the spring force, like the actual force that the spring is exerting, is against that. It's just to remind you that the spring force is a restorative force that's acting against the applied force, okay? So don't just willy-nilly throw in negative signs in front of it, like when you draw a free body diagram. If you have the spring force, that's Fs, and you have Fg for gravitational force, and you're drawing a free body diagram for an object hanging off of a spring, don't just randomly make the Fs value a negative sign. You calculate the magnitude of it. You identify up as positive perhaps and down as negative, and when you do your math, you'll say that Fs is a positive value and Fg is a negative value perhaps. That negative sign is not to force your hand in saying whether Fs is positive or negative. It's to remind you of the force being restorative. Okay? That's all it is. It's not a forced sign. You don't have to take it. You just have to know what it means. If you happen to see it on equation sheets or in textbooks or online or whatever, it's a common way of communicating it. And really, this equation is what people often refer to when they're talking about Hooke's law. Because what Hooke's law says, Hooke's law for an ideal spring. Hooke's law says that an ideal spring will have a linearly proportional force to stretch length or distortion magnitude relationship, or linear relationship between distortion force and the amount that the thing has been distorted by. Some people are going to say, is every spring ideal? No. Some springs don't follow an ideal law. Some springs might have a graph that looks something like this, where after you've stretched it a little bit, it becomes apparent that it actually takes more and more and more and more force to get that spring to distort. But a lot of springs, if you don't stretch them that much, if you stay within a low stretch amount relative to this graph, if you just work within a certain range, a lot of springs will follow a fairly ideal pattern if you don't stretch them too much. Okay, so that's what we're going to do today. We're going to take some springs, and we're not going to stretch them too much, and we're going to check to see what their elastic coefficient is, their K value, the Hooke's law coefficient, and we're going to see how those compare between stiff springs and stretchy springs. Any questions? Okay, no questions. Motion carries.